Thanks, everybody. Thanks for sticking around to the last talk on Friday. I'm all that's in between you and the weekend, so I take my responsibility seriously. Yeah, I want to thank all the organizers. This has been a wonderful workshop. I do get the benefit of having all of those talks having now gone before me, so I won't have to explain sort of any of my topics in any great background detail, which is great for me. So yeah, I'm Adam Holmes. I'm at NVIDIA Quantum. We're a relatively new and growing group. I myself have been at the group for about a month. And so this talk you will experience one of two things, or perhaps a combo. One is that all your context is already loaded from all the prior talks, and so there won't be much technical detail in terms of like the backgrounds of quantum error correction and things that we don't need that now at this point in the workshop. Or you'll experience that I've been at the company for a month. So one of those two things you might experience. Okay, today I'm going to go through sort of an introduction to NVIDIA Quantum, kind of our team strategy, our focus points right now, and in the context of this workshop, our vision for what it means to bridge sort of the NISQ era with fault tolerance. And the really brief answer to that from the NVIDIA perspective is that tooling is the answer to that question. How do you bridge all of these different systems that are currently getting designed and built iteratively more and more rapidly, it seems, because I'm less and less able to reuse slides these days, which means the field is progressing faster, which is cool. The answer that our team has for how exactly we enable the actual fault-tolerant quantum computing era to begin is through tooling. I myself have experienced the use of really well-designed and capable tools like STIM. When they come out, they greatly shape the way that we all do research, and they accelerate the way and the rate at which we can do good research. And I think that's really important. Our team also thinks that's very important, and so you'll see a view that we have, and that view is manifested in some new tools that we have and that we're sort of broadly offering with our sort of view on how quantum computing is developing. So you'll see those tools, you'll see sort of the structure of how those tools enable some sort of key analysis and development in fault-tolerant quantum computing, some very key sort of like study areas that I'll point out, and then some future roadmaps. All right, so this is a really cool slide with no details on it at all that I like to show at the beginning of these talks. It's intended to kind of give you the spirit of kind of how NVIDIA approaches research, and I'm learning this too, as I'm so new to the group. The spirit here is really that through the course of computing and as it's developed over time, different key components of computing stacks, from scientific computing to deep learning to generative AI and everything, those have all been enabled by hardware structures and software programming models that the NVIDIA company has been able to produce and give to the communities. I recently have learned some of the lore of NVIDIA, and I think I'll share a little bit of it because it's kind of exciting. The informal motto of the company is that our company is 30 days from going out of business. It might be more or less true now than it was in the past, but where that came from was the fact that sort of early on in like the late 80s and 90s, the company was just purely a graphics company, right? And they were producing accelerated graphics processors to do video gaming in PC land. And they had a contract with the company known as Sega at the time, if anyone remembers or knows that company. And that contract was to do two things. Sega would port some of their new video games to PCs, and NVIDIA would instead, or would sort of in return, build an accelerated chip for them to use in their next consoles. What happened as a result of that contract, NVIDIA actually sort of made a few different choices than the 3D graphics processing world did. And they made a choice to render things with curved surfaces instead of triangles, and a choice as simple as that can result in some pretty negative downstream things. They sort of got outpaced by the rest of the graphics industry for a while. And that contract ended up being the one lifeline that the company had to get them through into the early 2000s. They continued with, they got through that hurdle, and they continued with graphics processing units and building the first sets of GPUs. And in, I think it was 2012, when Jeff Hinton's group released AlexNet, the reason that AlexNet was able to actually do backprop at the scale that enabled it to be effective was because it used like two GTX 580s in a SLI config. And because of that, AlexNet worked. And once AlexNet worked, then it grew more interest in GPUs. And Jensen delivered the first, I think it was a DGX-1 to a room in, I think it was Silicon Valley with Peter Thiel in it and Ilya in it and some of the other OpenAI founders. And that was basically the story of where we are today, is through these weird little hiccups in time. But the point that is a kind of a little bit of a through line that you can draw in there is that at every step of that, NVIDIA's perspective seemed to still be where can accelerated physical compute change the game in different ways. It was a long intro to this little line now that is not connected to anything yet. Hence, there's no bridge built. This is my connection to the workshop, very viscerally for you. And I think the main thing I want to convey here is that NVIDIA has this perspective now on quantum computing that's very coupled to the way it sees accelerated computing at large. All valuable quantum computing applications are going to be hybrid. That's sort of principle number one. You're going to have some interface between where you're doing a ground state energy calculation or a fission calculation or opacity computation for, from what Andrew spoke about earlier this morning. You have some connection between that and a classical co-processor that itself is going to need to be, on the scale of petaflops, right? It's going to have to be a very large, very efficient classical co-processor that needs to interface tightly with that machine. There's a huge benefit in addition to this of building out a developer ecosystem. I'm not going to do the Steve Ballmer, but developers are key to all of this. Thank you, some of you. The CUDA programming model is something that I had known a little bit about before coming to NVIDIA, but it really is like a programming model through and through that changes the way that you think about how you write your programs. We have played with that in the quantum computing space quite a bit in different groups. I myself, in Fred Chong's group a million years ago, worked on this tool that was an LLVM compiler that I think is still ongoing in some form or another, where you would actually sort of define basic blocks in a true compiler sense that were kernels for the actual quantum components of an application. And then you want to interface those kernels with an actual classical control flow on the outside. How do you actually run that type of system? Getting the programming model right is sort of the key thing in enabling that to work. So NVIDIA's approach, and actually I'll say that at this workshop, the first thing that I've been asked by anyone I've met here who for the first time has been, what is NVIDIA doing in quantum? So actually, this is my whole goal with this talk is for you to not need to ask me that question anymore. And for when someone else asks you, you have an answer. All right, so I'm diluting the number of times I have to say this, which is great. The mission really from NVIDIA's perspective is to build a platform for heterogeneous CPU, GPU, QPU integration and development. The other principle there is to really accelerate all layers of the stack to enable useful quantum computing. And what that means to me, this is sort of a cultural thing that I need to shake off a little bit, having been at a different company before. fundamentally, we're not competing with any of these other products right now, right? Fundamentally, NVIDIA's perspective is if you have cool research you want to do, if you have a cool system you're trying to build, if you have cool software that you're building, a cool new decoding platform, NVIDIA wants to be there to help support you, make it faster, make it better, make it more resilient, make it more robust to errors, and make it sort of full system scale at a pace that maybe each of us on our own couldn't get there as quickly, right? That is the whole goal. So coming from actually I was at HRL Laboratories before, which is very much a sort of contract R&D company, and that's a very different culture. And so for me, this is new. For some of you, this might be a new kind of way to view how NVIDIA is interacting with the quantum community. But I do want to impress upon you that sort of this is how I want to engage with everyone else kind of moving forward is I want you to look at us as a resource, right? If there's something that a suite of GPUs could enable you to do that you couldn't without it, I want to know about that, and I want to help you achieve that. That's the whole strategy.
Can I ask a question?
Yeah, go ahead.
Do I call you on the phone? Like, how does that work?
Yeah, you call me on the phone.
Okay.
Yeah, you got my number.
All right. That was actually a serious question, though.
No, for real, I have an email address that might not be on the slide at the end, but I'll put it on the slide at the end, so you can contact me. All right, so with that, I'll go into some tools, and what I'll talk about are a few different pre-existing tools that you can actually now go and download and start using as you please. And you may or may not know about them. I myself was not very familiar with a lot of these. I think that I'm trying to help rectify that right now. Here's a really cool artist rendition of what these things look like in my head as well. Okay, so there's 4 kind of sets of tools right now that we as NVIDIA Quantum are sort of maintaining, offering, and helping to facilitate distribution of. The first is what's called QQuantum, pronounced that way, as I've learned. This is a set of proprietary accelerated quantum simulation tools to use GPUs to do certain types of simulations faster. These things are not open source, but they're open access. And there's a few different tools in that set that I'll talk about here in a minute. Next below that is CUDA-Q QEC, along with a set of solvers. The way to think about this is actually like open source QEC tooling. I don't know how many of you have had this sort of situation, but when I sort of get onto a new system and I'm on that new system and I want to do continue some of my research projects, I always tend to write the same sets of library functions first. And there are things to build me very basic canonical stem circuits and things to do mod2 RF functions. Simple things that some libraries now exist. You can download LDPC from Joschka Rolf and use some of those functions in there, but sometimes I like to write my own. The intent here is to at least from my perspective, do this once so that I don't have to do it again. And what's in there are a set of very useful tools that I find very useful, and we're continuing to build out. And so I'll talk about those as well. And then CUDA-Q, below that itself, this is the open source software platform that we really think of as the beginnings of a programming model. Some might say, hey, is it too early to define a programming model for these systems? The answer is maybe. But the only way you know that is if you try and you learn where it's deficient and then you keep iterating on it, right? And so this is us doing that. The last one on here is something actually real in terms of physical space. It is a hardware open architecture that we've built and delivered actually to a bunch of different hardware startups. I'll actually talk about the architectural floor plan of this, and it's a tool and platform that helps you integrate between sort of classical controllers, fleets of GPUs, and sort of outer system level controllers as well. So that's less in my area of expertise, but I will say mumble FPGA as well as everyone else has when I hit this point. Yeah.
So in QQuantum, it says running stuff on GPU, but you mentioned Slim running CPU.
I did.
So what does it give me? Do I need a GPU to run?
Thank you so much. Yes. Actually, so you mentioned CUDA QEC, right? Because that's where I said STIM. Not all these things are like, let's run everything on GPUs. I guess maybe I'll back up also. That is not the intent of these tools. These tools are not here just to say, hey, take all your stuff you're doing and please run them on GPUs because that's important to NVIDIA. That is not the message. The message is sometimes GPUs are very, very helpful. There's tooling to help enable that. There's also just other open source tools that should make writing STIM easier, should make integrating with custom decoders a little bit easier. That's the whole point. Yeah.
How do I interface with these tools?
How do you interface with these tools? Wonderful question. Well, there's a number of different ways. The main way is to download them and use them. There's a couple of QR codes and things in this slide deck. Is that what you're getting? Like,
No,
how to use
I was
them? What do
trying
you
to get
interface?
more along the lines of I have my own software that's already written in a separate language. How do I interface with this? Because I've tried to use this in the past, and so far the only bridge that I've seen is like COSM 2. Can we at least please get COSM 3?
See, I mean, yes. So yes, these are the questions that I think I'm now getting answers to.
Okay. Sorry, I don't want to ask.
No. I think it's important to maintain like bleeding edge compatibility. There will be like the model will never be for like all of us in this room who are doing cutting edge research. The model will never be that like these tools are ahead of us, so I just need to use the next one because fundamentally you're doing things that haven't been done before, right? That's not the intent of these tools. These tools are mainly there to make things that you do regularly much easier. Right.
Yeah. On the previous slide, can you speak to what open architecture means? NVIDIA is a hardware, it's not a software.
That's right. Yeah. So if you think about like what open architecture meant in like the early IBM clone days when PCs were getting built, so like there was a closed architecture that IBM had put together, and then there were also like these sort of other PCs that were getting built and distributed, I guess in like the 80s. Maybe before that, where the architecture was open, and what that meant was you could bring your own components. You could, here is a motherboard, and here is a RAM stick that you can't buy anymore because they cost $1 million and no one has them. But the point, what open architecture means is that the schematics and the actual structure of NVQLink is open. So you can see it, you can plug in a controller that you have for your quantum platform of choice into one end of it. And into the other end, you can plug your server rack and control, and through the appropriate drivers that we would build together. There are some that exist as well. You can build a system that's fully integrated. Right.
So you can, like, what things you can control, like connect the FPGA to?
You can. I have a slide in 1, 2, 3, 4 down the road here that like actually has the floor plan. You can see it. Yeah. Okay. So here's a little bit about cuQuantum with a bar chart that's actually, it has no actual axis on it, more fun marketing stuff. The libraries, so the other thing that I've learned is that, so stuff from NVIDIA with a Q in the front. These are like typically like very highly accelerated GPU kernels that are by necessity closed source, but there's open access to sets of functions that let you run them. So like there are 5 of these tools that exist in the library for accelerated quantum sims. They range from state vector sims to polypropagation sims. There are Q stabilizer sim tools that run on GPUs. So, those are useful for certain things. Usually, like the noisy Clifford sampling is not the hardest part in your simulation toolchain, but it does actually speed things up over a CPU-driven STIM workflow. Yeah, go ahead.
So suppose I want to do like some density matrix or some state vector simulation. Am I limited by the memory on my GPU or like the overall system memory?
So are you saying you have multiple GPUs that all have their own independent memory, and does that give you a unified memory access?
Yeah, because I guess as a poor grad student, my GPU is not that good. So yes, very little memory compared to the total RAM on my system, for example. So does this libraries do some kind of streaming between the RAM and the GPU memory, or am I limited by just the GPU?
I believe you're going to be, off the rack, I think you're going to be limited to your onboard GPU memory. There's tooling inside the CUDA-Q interface for like CUDA-Q real-time stuff, but that's mainly about like actual real-time decoding workflows. I don't think anything has been written right now that lets you stream from, say, your like CPU RAM on chip to your GPU memory, sort of on the fly. But that's a great thing to ask for. I'm not sure how well it can be done, because that is the bottleneck when you're running GPUs typically, is the loading of the kernels, and actually executing after that is easy. But if you could stream into the memory and then actually just compute like use a regular like, execution queue, that does work for a lot of things. So these, I'm not sure if they have that in them, but I can find out. Yeah. Yep.
Say, for the sake of argument, instead of being a poor grad student, you are a wealthy industrialist with access to H200s.
Okay.
Right? Are there any benchmarks we're going to see for this like Q stabilizer product against STEM? Because that would be super duper interesting to me. And knowing how they would speed it up over STEM, like do you just run many shots in parallel or something? Like.
So, yes, there exist blog post write-ups about those simulations that have been done. There don't exist any white papers yet, to my knowledge. Again, though, what I said at the top here, the actual details of how the mapping to GPUs is done is not, like, that's going to be a closed source thing. So half of an answer for you. There do exist those blog posts, and I think, good, okay, sounds good. Right.
So sorry.
Yes.
The part that is counterpart to STEM is closed source.
So yes, all of this on this slide, these are all closed source accelerators. So Q stabilizer is the name for the package that just does noisy Clifford simulation. It sort of has the same type of API to build those circuits and run them. It just does optimized mapping to GPUs. Yeah. Gosh, I thought that was the last talk of the last day, and you guys are still hitting me with all these questions. Okay. CUDA-Q, QEC. By the way, no, I like the questions. That was a joke. The other thing, let me just go through this. What CUDA-Q, QEC is, because these tools are interesting to me. They don't have all the features that I want yet, and so I'm helping to build more of them. And there is a lot of cool stuff in here. So one of the things that it has that's interesting is an API for real-time decoding. Those sounded like buzzwords to me before I joined the company and understood what it meant. But like fundamentally, what these actually are real defined kernels to help you load a GPU and actually do this type of like kind of streaming NQ, DQ decoding protocol that otherwise would be pretty complicated to build yourself. So those are, this is now, I'm talking about open source tooling, right? So all of this is now open source. Yes?
I'm sorry, NQ, DQ?
To enqueue stuff into your execution queue and then to dequeue it out of it.
Oh, not
Sorry.
the letter
ENQ,
Q. I'm so cooked by all these acronyms. I
Sorry.
hear Q and I think of Q. Yeah. Okay.
Yeah. ENQUE. I don't know if you can see mine. Yeah. So there's tools to help you if you want to design and simulate a real-time decoding system. Useful, helpful. Yeah.
Does that also include decoders themselves, or? It
includes a couple decoders and like a few different infrastructure pieces to help you bring in your own decoder to that thing and try it.
So you have to have a GPU accelerated decoder already, but it'll help you link that to your systems, or like you can bring
Yes. So do I have a list of the decoders? Yeah. I might have a list of the decoders in here. Yeah, there's a few. So there's a couple that like are just sort of stock decoders, right? So there's like a GPU accelerated relay. There's a tensor network decoder. There is sort of a stock BPOSD decoder in there. There's this thing, which is a package wrapper around an AI. So what it is it'll take an ONNX file describing like some particular machine learning model in a standard form, and then it has a built-out API around it so that you can just query it like a decoder and have it solve certain types of decoding problems if they're appropriately like structured.
I'm saying when you put this like build your own decoder, non-decoder stuff, like, are you imagining someone brings in a CPU decoder and it helps you GPUify it, or they write a GPU accelerated decoder and this helps you link it to the rest of your?
It's more the latter than the former. Yeah. This is not an automated tooling set to GPUify things. That may or may not be something that we're working on too. But yeah, yes.
So can I use my own noise model?
Absolutely, yeah.
Okay. Has anyone tried using a non-Markovian one? Is there support for that?
So, like running an actual non-Markovian noise model through this. Typically, this is set up to do like noisy Clifford sampling, because I do that a lot. But you can write down circuits that you can then run these simulators on, right? So like you can actually run a density matrix simulation with some version of your favorite non-Markovian noise model. It would probably use that, and it wouldn't use, one of the noisy Clifford things, right? Because you can't.
Yeah, we've driven, just to back you up, we've driven QQuantum with a complicated noise model.
Cool. Appreciate it.
The Onyx file that the AI decoder gets is the decoder, the model, like
Yes.
the AI model.
Right.
Oh, I see. But the tool is like kind of benchmarking around an AI model.
The tool. So the tool is my vision of what the tools are is just a set of things that you can then go and build your experiment out of, right? And one of those is a nice clean wrapper around what you could call an AI decoder, but you bring your own Onyx model to it, right? And so you could, I could write my STIM circuit once. I could say, hey, we're going to use STIM as a backend, which it supports. And then I could say, hey, all right, I want to sample a whole bunch of times, and I want to do offline decoding, and I want to try 3 different decoders. I want to try regular pi matching. I want to run this, pick the tensor network one, and then also this AI decoder one. The tooling gives you API calls to do all those things, right? So it should just be a little bit simpler. Right. Yes?
So I remember for STIM, the reason for it using CPU instead of GPU is because of sparse matrix multiplication.
Yep.
For here, like in the package, is GPU acceleration more important to circuit simulation or decoders or decoders?
Where is it more important is the question? Yeah, it's definitely more important to types of applications that are nicely data parallel. Now that's almost a circular answer for you, but you're right that like STIM being primarily written to vectorize and SIMDify simulation sweeps, like that does map really well to CPUs, right? I think there are nice mappings that also work to GPUs to do noisy Clifford sims. That's what QStabilizer is. I think it does help there. It's very, very helpful in the things like state vector simulations, density matrix simulations, things that have a lot of like MATVEC products, matrix vector multiplications, things like that. It's great at accelerating those things. Things that naturally map to tensor networks as well. It's great at contracting them. Some decoders look like that. Some circuit sims also look like that. And so for those things, it's good at those sets of things. It is definitely not uniformly good at all of them. So part of this, part of it being this like little set of tools is to help, you pick and choose what you want to do. Okay, I will go into CUDA-Q now. So this is more of the programming model itself. This is us taking a stab at defining what it means to write a program that has sort of classical control flow and processing in conjunction with some set of kernels that runs on an actual quantum processor. This is mainly like a slide telling you, hey, look, it's a bunch of these different partners have run them. I think for this audience, it's still like a very open research question to me, like what that interface should look like and what the programming model, how it should develop. This is an attempt at it. what Q to Q is, and I guess I do have a slide that goes into it in a little bit. But for now, I think like the main thing to take away here is that it's really just understanding what this is, right? To me, like I didn't understand the differences and the distinctions between Q to QX, where Q to QEC lives. Those are the libraries. And then QQuantum, which is all the accelerated simulators. Those are all different things, right? And this is a programming model that I do encourage everyone to like go and try. This is your promised floor plan of NVQ-Link at a very schematic layer, right? It's not an actual floor plan. But the whole model here is that there is some physical quantum processor that has some controller associated with it, right? So the stuff that NVIDIA actually brings to this NVQ-Link are the main architectural connections. They stop really at the controller itself. And this is a thing that's like, us as NVIDIA, it's very challenging to go and get into that layer for some hardware builder, right? We would certainly, and we are kind of partnering with a bunch of different platforms to help with that. But from a like build once and deliver perspective, the open architecture of this is really set up so that you could have a slate of different types of controllers that all maybe control like different physical quantum processors. And what these controllers do is they hook up through this Ethernet switch to a real-time host that itself has a bunch of real-time APIs. So this is how you can do like actual real-time decoding in a physical structure that itself like, it's an open architecture so you can bring in components to it, but it is also physically defined and is there. It has nice things like less than 4 microsecond round trips between the physical QPU layer through all these switches. It's controller dependent, but we've demonstrated for microsecond round trips from here like through to some of these like GPU accelerated real-time APIs. There's like 400 gig Ethernet switch in there. Bunch of other nice properties about it. But yeah, so this is a real like physical platform. Okay.
Like a real physical platform like this exists.
Yes.
You built it.
Yep.
Cool.
It's out there. I didn't build it, but we built it.
Yeah, everything except the QPU, I guess.
That's right.
And you have some mock QPU?
Well, so it's plugged into several different QPUs. Like it's been given to different hardware partners.
We'll talk about this later.
Yeah, there's some slides I have on that. Yeah. Yeah, so that's a measurement of the time it takes to get a signal sort of from here through these switches into a QPU and back, or starting from a different place in that loop, right? Now, does that include like decoding? No. This is just a measurement of this particular system. Yeah.
Since the physical QPU is at a different site, does that 4 microseconds include the time to get to the physical site?
It can be at a different site. Usually it's not. Usually it is very co-located. So these things are physically built and handed off to partners at their sites.
Oh, do you know, are you free to say who has purchased these systems?
Among them are these. There's a bigger slide in some other decks that I have. There's at least 17 different groups that have NVQ-Links.
Interesting.
Yeah. Yes.
So what kind of Ethernet is this? Because commercially I've only seen 10 gigabits.
I don't know.
Okay.
Don't know that answer. I bet the internet does. Okay, we're going to speed up a little bit so that I can get through some of these other slides.
When it goes to 0, you have 10 more minutes for
That's right, thank you. Yes, we are doing questions just throughout, so I won't stop for the question thing. Okay, so this is a little slide that says, okay, a lot of this stuff integrates together. You can like write circuits in CUDA Q that use tools from CUDA QEC and uses backends that are like Q stabilizer simulations or Q state vector, depending on what you're doing. You can also compile straight through like NVQ-Link to get real shot data, and all these things like work together, and that's the whole point. There is a QR code on here, and I can put it at the end as well. Like, it's just, if you Google CUDA QX or CUDA Q, you'll find it. Okay, so these slides are a little bit more like philosophical about the thoughts behind how do you accelerate quantum processing units as a system. I think in the sake of time, I'll kind of go a little bit fast through these. Some of the questions that we as NVIDIA are thinking about are like, there's different levels and different layers of accelerations that these systems are going to need. There is some actual classical supercomputer that's going to sit alongside a real quantum processing unit. What does the architecture of that thing need to look like? There are physical accelerations that like individual quantum processing units themselves could use. How tight is tight coupling? What does that actually mean? When you support multiple different physical QPUs, right? These are all the shapes of qubits. I don't know if you're familiar with these shapes of qubits before, but we saw these in Maddie's talk, these circles. So, thank you. The main point here is that like there's a lot of different requirements that all these different systems have, right? And when you think about how do I build a system that like helps solve some of the hard problems that all of them share, you end up thinking about compiler stacks, and a lot of different groups are thinking about compilers. We are as well, and those thoughts have begun to coalesce into different decisions that define what we're calling, what is the intermediate representation inside CUDA Q, which, if you're familiar with the LLVM universe, MLIR is sort of the basis for a lot of that. A couple of folks on our team came from Oak Ridge National Labs, Alex McCaskey, who you might know, Justin Leitz, and others. And so they spend a lot of time developing things like XACC, which is another acronym for something. And it's a compiler tool that, alongside my version in Fred's lab, SCAFCC, tries to solve a lot of these problems by making a lot of decisions, right? And we are continuing to do that in different ways. I do want to get to kind of some of the other types of work in this deck. But like, I guess you can conceive of a really simple version of this problem when you're thinking about like the programming model that I need when I want to compile to a quantum processor. There are lots of different ways to lower instructions to different types of physical systems. This workshop has been fantastic at covering a lot of different things, from the sort of application layer all the way down through quantum error correction. What at least I've found conspicuously absent is really any thought about like what the instruction sets look like on controllers, right? And sort of what type of instruction bandwidth you're going to need on controllers that are maybe going to actually run systems. This is not that. This is one level up from that, but you still, those questions are ones that you need to answer sort of at this layer. Things like, how do I appropriately lower instructions that I maybe write in like a unified kind of C-like language to a set of different types of controllers, right? So we've done some of this, and we've actually built some of these systems. I'll kind of get to something else that has been documented and is kind of public now, where we did some real-time decoding collaboration on Helios. There was the CUDA QEC library was used. The BPOSD decoder was in there, and it had a nice decoding time. It helped bring down errors in the Brings code, 38.3 code. Not quite the 10.5.3 code, I think, was but yeah, go ahead.
Just when you say median 67 microsecond.
Yes.
That's, I assume, per round.
That's per round, I think, yeah.
You know what your latency was?
I don't. This work predated me, but yeah, I can find out. Okay, so this is a concrete slide to sort of solidify the fact that like what we're trying to do is think about these systems really hard, make some design decisions, deliver something to help actually run something on a quantum processor, take a look at what it did, and iterate on that process, right? Trying to solve problems that maybe help accelerate and move hardware companies along faster in their roadmaps. Yeah.
Sorry, I'm a little confused about you say without decoding, with decoding. Without decoding, it would be pretty.
It would be pretty bad. You see like a 5% error rate there, yeah.
The logical error rate without decoding. Oh, okay. Okay, yeah, I guess
so
that makes sense.
This isn't anything crazy.
No, I get it. You got 30 qubits going, and it's like, okay, cool.
Okay, right. So the other thing I want to mention is now just switching gears kind of a little bit. I personally was sort of a skeptic of a lot of the machine learning tools that we have now, up until maybe about a month ago. Something changed for me. You maybe guess what it is. What it was that I got to use them. And I'll tell you here, surprise, surprise, this graphic on the right is all Claude generated. This is just Claude going into our CUDA QEC deck and saying, hey, outline like some of the key protocols in here, how they interact with each other, and list out some important things of each one suitable for like a presentation like this. For a Friday afternoon, I said. And it's pretty good at these types of things. It's not good at everything, but the point of bringing that up is that we have really powerful machine learning tools now, or artificial intelligence tools, depending on your dialect. And they've been demonstrated in a lot of different like sort of small papers. But what I want to mention now is like, we're building a lot of compute in the world. And we can start to leverage that lots of compute in new ways. This was a study that was done, I guess, at LBNL. And what these were actual like electrodynamical simulations of floor plans of superconducting chips using the Perlmutter machine at NISQ, which has in its full system like 7,000 GPUs in it, right? And so like this type of modeling, I'm bringing this up not because I know much about this, I really don't, but I'm bringing this up because like the scale of compute that you have access to now is different than it was even just like a year ago, right? And so there's lots of new things that we can do that we as NVIDIA are trying to like actually enable, like really right now. One of them that people in this room probably have seen was that there was a sort of a Chinese group who came out with a set of cultivation simulations using a set of 16 H800s for 3 weeks to do sort of extended stabilizer simulations of magic state cultivation, components of cultivation. I think they skipped the escape stage. But the point of this is like, these types of sims just like were not accessible before, right? So we're going to be able to simulate things at much greater scale as long as you can like have the tooling and the know-how to express your simulation sets in ways that allow you to use a suite of 16 H800s. And that's not easy, it turns out, I'm learning. So this is to demonstrate that those simulations exist. The other thing is, and this is more me speculating, and like I am primarily a quantum error correction theorist, and so I've come to NVIDIA to help with, thinking about a lot of these products and thinking about a lot of these tooling developments, but also thinking really deeply about designing quantum error correcting codes in this new world. This is just a few codes that we know about. This is the Beryllium code from Microsoft that they came out with over last summer, along with a few different others, just for demonstration's sake. But it's, as you probably know if you are in this field, like it's very difficult to do this type of work at scale, right? So it's very difficult to pick a code, design the circuits you want to benchmark, run noisy simulations to actually calculate performance in different regimes, and back out things like logical error rates at physical error rates you care about, and like pseudo thresholds of different gates. Really, fundamentally, what I mean, what this is all about is like thinking about and properly benchmarking logical instruction set architectures, right? So like the gross code paper was a fantastic paper that I think has gotten a lot of people starting to think about what ISAs look like at the logical level. Thanks. And since then, there have been many more such papers. This one being one of them. The Pinnacle architecture paper is another very interesting one. And there are notable gaps in a lot of these papers. And mainly they come from, in my perspective, sort of a lack of tooling. Like if you had all the tooling, or maybe strategic decisions, but if you had all the tooling, you should be able to like define a code, define your instruction set architecture, and benchmark that entire thing with a simulation suite, right? And that's how you do large-scale system design. That's how people build airplanes. That's how people build rockets. And what we're doing is much harder than those things. Since none of them are here, I can say that. anyway, that's the point that I want to make with that. Yes, go ahead.
I was curious about this. There's a bullet point on more efficient logical operation sets. Could you comment on?
Yeah, so more efficient logical operation sets. There are a lot of different ways to do logic in encoded qubits, right?
Yeah, but like, are they supported?
Are they? Well, that's the question. The question is, for any specific code, what is available transversely, what is available through different types of gadgets, and how well are those gadgets performant in different systems. So, you can imagine a very simple example is to think about, T-state cultivation in surface codes and comparing that to magic state injection in gross code architectures, right? Which of those is more efficient from a computational workload perspective, right? That's kind of what I mean here, is doing holistic benchmarking of these things to really make informed decisions about logical instruction sets. If you're given a suite of like physical qubits, how do you make them work, right? That's what all this means. There's been a few pieces of work about like using different learning methods to find new codes. This is like a pair of papers from 2023, I think, talking about using interesting projective simulation methods in reinforcement learning agents to find new codes. Those are interesting. I think it found a 1917 non-CSS code, which is pretty cool. 2317 is usually the distance 7 small code you think about, but it's CSS. So I bring this up because like this was work that really predated a lot of the like big data, large language model world we live in now, right? And so like, what is the analogous version of this paper that you might think about performing today in terms of research? One of them was on a poster out in the lobby, was this Phantom Codes paper, very cool paper. Authors somewhere in here, I think, maybe. Yeah, there you go. I didn't do the Michael Beverland thing and take a picture of all of you, but before my talk, which I should have done. Anyway, the very cool paper did a lot of very aggressive like data collection work, right? I think you say it took like a month and a half to get 10 terabytes of data, something like that. Very cool data set, right? And you go through it specifically looking for like pairwise CNOT transversal gates. A lot of things you can do with a data set that size, right? I'm going to ask you later if I can get access to that data set. I won't do it now in front of a large audience. All right, last couple things here. I want to bring another paper up just because it's like a totally different lens on designing better codes. And this one was a paper that came out very recently as well, thinking about like designing a code from the perspective of I want BP to do well on this code, which is actually like how we think about designing LDPC codes for wireless communication classically right now. They're driven mainly by the decoders. This paper tried to do the same thing, thinking like decoder first and backing out a good code from that. There's some details on how it does it, like trying to puncture codes in ways that don't actually add logicals, which are pretty cool. I encourage you to go take a look at it. It gives you a code that's very different than, like in a different regime entirely than we're used to thinking about, right? The smallest code I think they could find was like order 10,000 physical qubits, order 5,000 logicals. So now at this point, and a distance of like 48. So these types of codes are really interesting to think about from a full system perspective. What could we do if we were going to encode everything all together? Can you do that? Can you actually build an efficient instruction set architecture that can do maybe lots of stuff transversely? Turns out, no, you can't do everything you want to do transversely. Dan Gossman proved that a week ago. So the theory is also leading the way here for us. If you haven't seen this paper, you definitely should. Pretty cool paper, pretty made me sad kind of paper. But he proved that there's no stabilizer code that encodes more than k equals 2 logical qubits. No such code can support a fully transversal implementation of the Clifford group on all those logical qubits, including if you allow for like cutting out little k-fold transversal gates. So important, cool paper that shapes how you might go through a space of codes that's this big, right? Maybe you're looking for different things. Yes?
You can add permutation and achieve fully transversal.
Even with permutations, you can't do it.
There was a paper on achieving the...
So you can do a lot. You can achieve like a big group of encoded operations using permutation groups, absolutely. What this paper proved is that you can't achieve the full encoded logical Clifford group on all of your qubits. So if you have even down to k equals 2. So if I encode 2 logical qubits, I don't have access to the full logical Clifford group on both qubits.
I think I saw a result on QRM codes.
So that may be a
I have an
generating
answer
set
for
of
that.
Clifford.
Set of Clifford.
Like generating set of Clifford. Here it's talking about full Clifford.
I think that sounded right. I couldn't really hear, but yeah.
The answer is that the QRM paper, they compose different fold gates. If you compose 2 fold gates, you get a K fold gate. So they're consistent with each other. Conclusions.
Okay, that brings me to the end. I will stop on this slide. So there's sort of a real-time stack of stuff that we're developing and coming out with too to help do more of these types of real experiments in the future. There's Q2Q. This is a QR code to get you there. And yeah, I'll stop there and thank you for your time.